Hi everybody, this video is a continuation of our discussion on section 6.2, the standard normal distribution. In our last video, we talked about the distribution, how to compute z-scores, and how to find the area under the curve to the left of the z-score, because that will produce for you the probability that the random variable z is less than or equal to the value z. Which, by the way, is going to be equal to the probability that the random variable x is less than or equal to the value x for the case where z happens to be the z-score of x. And this is exactly what we're talking about here. Here is the probability of x being less than or equal to x for a certain normal distribution. And this is the probability of z being less than or equal to z on the standard normal with the associated z-score, and they are the same. Well, in this video, we're going to talk about how to compute the area under the standard normal curve to the right of z. And when we do that, what we're doing is we are trying to compute for ourselves the probability that the random variable z, a standard normal, is greater than or equal to a particular value. In this case, the area to the right of 1.37 is going to be the probability that z is greater than or equal to 1.37. Okay, well, here's the crux. The tables that we have only give you the area to the left of the z value. So you give it a z value, it will compute for you the left. Okay? But we have one thing that's working for us, and you can see it here. This is 1.37. This is the area to the right. This is negative 1.37. This is the area to the left. They are identical. Why are they identical? Because the standard normal is symmetric about 0. So as a consequence, if we want to find the area to the right of a certain value, that's going to be equal to the area to the left of the negative of that value. Or more precisely, if I can find where my, there she goes. More precisely, the probability that z is greater than 1.37 is going to be equal to the probability that z, she's greater than equal to, is less than or equal to negative 1.37. And this we know how to compute from our previous video. We just look up negative 1.37 on our tables, and that's our answer. So how are we going to do this? The first thing we're going to do is we are going to figure out what negative z is. We're going to use our tables to figure out the area under the curve to the left of negative z. We're going to compute this, which is identically equal to that. Negative 1.37, we're going to use our normal table from negative infinity to negative z. 1.3 there, 1.39, 1.38, 1.37. Just remember that if we're dealing with this table, we start at 0.9, we go down to 0. The other table, we start at 0 and we go up to 0.9. Okay, and we do that to make sure that the areas continue to increase. So there we go, negative 0.0853. That happens to be our answer. How can we do this using our calculator? Well, to find the area under the curve to the right, we're going to use normal CDF. And for our calculator, it is much more straightforward. Let's just go ahead and get our calculator up. Where is it? There she is. And this is how we can do it. It's even much simpler in this particular case, except for the one little detail that we have to be careful about. Just go in the second, distribution. We're going to do normal CDF. There it is. Now, remember, our lower value is going to be 1.37. So we want to put in 1.37. Okay? Our upper value is going to be as close to infinity as we can get. Well, the closest that we can get to infinity on our calculator is 1 times 10 to the 99th. Okay? And in our calculator, we can write that in as 1 E99. Well, actually, in our calculator, we can do it both ways, but I'm going to focus on this way for the time being. How can we do that? Okay, well, first thing is we need to go down to upper, and this is how we can do this. Type in 1. You see this little EE thing? That's what we're looking for. Second, comma, there's our E, 99. Okay, hit enter, and this is exactly what we're looking for. Our mean is 0, variance is 1, paste, and there you go. And we have 0.0853. Our fifth decimal place is less than 5, so we don't need to round up, and that is the exact answer that we had before. Now, the other way you can do this, for at least computing the higher levels like this, let's go back into distribution. Second, instead of doing 1e to the 99, I could, if I wanted to, just do 10 power 99. They're both the exact same number. Mean is 0, variance is 1, and we get the exact same thing. And this brings us to our last topic, which is finding the area between two z-values using a table. So here we want to find the area under the standard normal curve between negative 1.68 and z equals 200. Or I'm sorry, z equals 2. And so basically we want to compute all this area here, but we want to subtract, we want to make sure that this area is excluded. So how are we going to do this? Well, the first thing we can do is just find the area to the left of 2. It's giving us all this stuff right here, but it also includes all of the area to the left of negative 1.68. What are we going to do about that? What about if we subtract it away? If we subtract it away, then we have this. So how can you do? So how would you do that? Well, we can find the area to the left of 2. That will give us the probability that z is less than or equal to 2, and we want to subtract away this, which is the same as subtracting the probability that z is less than or equal to negative 1.68. And that's exactly what we're going to do. We're just going to compute those two areas and subtract them. So let's go ahead and find the area to the left of 2 using our tables. Well, you want to use, since 2 is positive, we're going to use this table. 2 is the same as 2.00, so here is 2.0, and that will give us 0.9972. There you go. There it is. All right, and that is what this area is. Now remember, we need to get rid of this. It needs to go. It's bad. It doesn't belong there. Okay, so we're going to go ahead and subtract that away. For here, we're going to. So now we need to compute z, or find the area under the curve for the case where z is equal to negative 1.68. So we are going to use the negative z sucker here. Negative to negative z. Going to go down to 1.6, negative 1.6. 0.9, 0.8, there you go, 0.0465, that's our number. And then finally, we are going to take z equals the area under the curve for the case where z is equal to 2. That's all this. We're going to subtract this area out, which is what we've done here, and that will give us negative 0.9307. Okay, so that's how you can do that using tables. And this is probably the one case where using tables is a little more challenging than using the calculator. How can you do this using a calculator? Let me show you. Exact same problem. Let me bring up my calculator. We don't need to see that yet. Second, vars, normal CDF. What is our lower limit? Negative 1.68. Negative 1.68. Enter. What's our upper limit? 2. Mean is 0, variance is 1, paste. There you go. And we have 0.9307. Next decimal place is also 7, so that will round to 0.9308, which is exactly what we got here and not what we had before. Now, why would that be? Well, the reason for that happens to be with precision. Notice the calculator basically computes it to a very large number of decimal places. However, your tables only go to 4, and then they lose the extra information. As a consequence, for this one, we end up with a bit of a rounding error. Which answer is actually more accurate or more precise? Actually, let's go with accurate. This would likely be the more accurate answer because it uses more precision than the other one does, or uses more decimal places. This one, in the table lookup, we are actually losing information because we are not accounting for all the values beyond the 4th decimal place. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. Stay tuned for my last video for this section where, yes, I get to do your homework. And until then, this is Bob Boyle, signing off.